Hey everyone, Mr. Schachter here with Continuity Part 1. Very excited. Use a continuity test to determine if a function is continuous and identify any discontinuities of a function. Those are the objectives for this video. Let's get started. First thing, very important test, the continuity test. Let's zoom in here. So the continuity test is broken into two pieces. Piece number one deals with an interior point. A function f of x is continuous at an interior point C of its domain if the limiting value as we approach C equals f of C, the function value. At an endpoint, we're kind of going to split it up into a partial limit, because if we talk about a left endpoint A, and then we consider the limit as we approach from the right of f of x equaling the function value at A. If we're at a left endpoint, we're like over here, and the function is like doing something over there. We can only approach a left endpoint from the right, okay? We can't approach a left endpoint from the left because nothing is to the left of it. So that's why it's kind of like flipped. The same thing goes, actually I'll just keep the orange. The same thing goes for a right endpoint B. The limit value as x approaches B from the left of f of x must equal the function value at B. Continuity test is easy as 1, 2, 3. Here are the 3 steps you follow. Step number 1. Does the limit exist as you approach C? Which basically is really fancy way of saying, does the limit as x approaches C from the left equal the limit as x approaches C from the right? Is this true? If this is true, then this exists, okay? And then step 2, does the function value exist? Or is there perhaps some kind of discontinuity there? And last, does the limiting value equal the function value? That's how you prove continuity at a point. Let's try some examples. Example 1. Determine if f of x is continuous at x equals 2. So you might ask yourself, why are we only considering x equals 2? Well, this piecewise is continuous everywhere else. The only questionable value is 2, because that's where the pieces start to jump around a bit, and that's where the bounds change. So in order to determine if continuity exists at 2, you first have to determine if the limit exists. So you need to ask yourself, does the limit as x approaches 2 from the right, does the right limit equal the limit as x approaches 2 from the left of f of x? You're trying to question this. You're trying to question this. Is this true? And if it is, you're in good shape. If it's not, you're done. The answer is no, it's not continuous at 2. Let's go ahead and try. So the limit from the right-hand limit, I need to use the right-hand side of the function, which is 2x minus 1. If I plug a 2 into 2x minus 1, plug a 2 right here, I'm going to get 4 minus 1 is 3. So the question is, does 3 equal the limit as we approach from the left? Well, the limit as we approach from the left is this guy. If I plug a 2 in here, I get 2 plus 1 is 3. Yes, this is good. This is yay. We have the limit value. What that means is the limit as we approach 2 in general, no partial limits, of f of x is equal to 3. So the question is, does this piece right here equal the function value? Does this equal the function value f of 2? Well, f of 2 is right here. It's 4. No, they don't equal each other. They don't equal each other. And that's enough information to simply say, therefore, these little 3 dots mean therefore, f of x is not continuous at x equals 2. Okay? It's continuous everywhere else on its domain, but it's not continuous at 2. Let's try another example. B here. Use a different color. Use a nice blue. So B here, if I check the limit values, okay, so the limit as x approaches 2 from the right, the question is, does this equal the limit as x approaches 2 from the left? Are these equal? Well, let's try. 2 from the right would be the bottom piece. If I plug a 2 in here, it's 2 times 2 is 4 minus 1 is 3 equals. The limit as we approach from the left, I use x plus 1, which is 2 plus 1 is 3. Yay. And what's the function value? Well, the function value at 2 is also 3, because it's the same piece here. This is where x equals 2, right? So in this case, yes, the limit as x approaches 2 of f of x equals f of 2. So f of x is continuous at x equals 2. And this guy's continuous for all points on this domain, which is really nice. Let's try C. C is really kind of easy to understand because it's almost the same exact function as B, but instead it's a 2x plus 1. And I think you can kind of imagine what's going to happen here. If you try to check the limit values, the limit value from the left, which is this piece up here, this piece, is going to be 2 plus 1. That's going to be 3. And that's not going to equal, if I plug a 2 down here into this piece, it's going to be 2 times 2 is 4 plus 1 is 5. So this is f of x is not continuous at x equals 2 since the limit as x approaches 2 of f of x does not exist. Okay, so since the limit doesn't exist, it can't be continuous. Right? If a limit doesn't exist, we know there's some type of discontinuity there. Okay? Okay. Let's take a look at a more formal example. This one says, find the value of b that makes f of x continuous. So really what we're trying to do is find a value that would make the function continuous. So we're not really sure, or we don't know that it's continuous right now. We have to make it continuous. Notice this right here. This kind of tells you what value to examine. The value we should be examining is x equals 1. That's where we're questioning continuity. So if we take a look, we know the limit as x approaches 1 from the right needs to equal the limit as x approaches 1 from the left of f of x. So this must be true for continuity to exist. Unfortunately, we can only find one of them. We can only find the left-hand limit, because the right-hand limit has a b in it, and I can't solve that. But the left-hand limit can be solved. If I plug a 1 in here, for x, I'm going to get 1 squared, which is 1, minus 3 times 1, which is negative 2. So the left-handed limit is negative 2. So the right-handed limit, 2x plus b, must equal negative 2. So if I solve for b, all I really need to do is just figure this thing out. Also remember that the value we're considering this at is x equals 1. So if x is 1, I can plug that in here and just get 2 plus b is negative 2. And I can minus 2 from both sides to get b is negative 4. So if this function has to be continuous at 1, the value of b must be negative 4. Let's take a look at some types of discontinuities that exist in the world. The first type of discontinuity is when you have some kind of a jump discontinuity. An example of this would be a piecewise function. This is when a function is kind of like trucking along and boom, all of a sudden it ends up over here like, whoa, what are you doing over there? It's a jump discontinuity right there, okay? A removable discontinuity is just like when you have a hole, so you've got a nice, clean, continuous function, but like right here, it's actually a hole, and it's undefined at that value. We call these removable discontinuities because you can actually remove them from the function, and that's something we'll look at in a minute. Infinite discontinuity is basically when you have a vertical asymptote, unremovable. And an oscillating discontinuity is when you have a function that kind of has an angle that'll have a discontinuity. And they look really wacky. They kind of look like this, where the function is kind of going at a good pace, and then all of a sudden when it gets close to that value that's going to kind of create a discontinuity, it like spazzes out in the middle, and then it kind of goes along in its nice, clean, happy pace for a bit. They're rarely going to come up. I just wanted to include them just so you were aware if you ever saw that. Let's try this example. It says, find the points of discontinuity and identify each type of discontinuity. The first thing you'd want to do is see if you could simplify the function. Looks like the numerator factors. So if we could factor this into, what's this? X minus 2x plus 1. This would factor. And then the denominator is the difference of squares, x minus 2x plus 2. It looks like after we do that, the x minus 2's cancel. Whenever you have a cancellation like this, this is a removable discontinuity, and that's going to be located at x equals positive 2. Of course, the question is, what is the value that would make this discontinuity equal to 0? And that would be positive 2. So positive 2 plugged into there would make 0. So that's a hole. This is a hole. This is a removable discontinuity. Additionally, you've got this thing right here. Actually, I'll use it different. Actually, we'll continue the function right here. X plus 1 over x plus 2. This right here, you've got another discontinuity. But this one isn't removable because this function is now completely simplified. So you have what's called an infinite discontinuity. And that's going to be located at x equals -2, okay? And what that is that's an asymptote. Specifically a vertical asymptote, okay? And just for future reference as well, this function, after you simplify a function and kind of remove a discontinuity, this has a special name in mathematics. This is called an extended function. Okay, so an extended function is basically when you remove some type of discontinuity and then the resulting function that exists is known as your extended function. All right? Let's look at an example of how to remove a discontinuity. So in this example, the numerator was factored. Numerator is factored, and a cancellation exists, which means you have a removable discontinuity at -5. And you have this negative x minus 5 on the bottom here, and that's going to be an infinite discontinuity at 5. But in order to create a function that's going to basically remove that discontinuity, you just rewrite f of x as a piecewise function, where the top piece is the original function. No cancellations, the original function. And it's going to be, the bound is going to be everywhere except the value that you have that removable discontinuity. Okay, so -5 was the place where we had the removable discontinuity. And then what you can do is the next piece, the second piece of your function, is actually just going to be the value of the extended function evaluated at the point of removable discontinuity. You just plug -5 into x and you get 11/10. And the location of that is the exact place where you checked it, x equals -5. This function that we created has no removable discontinuity. This piecewise function is completely continuous, except of course for the infinite discontinuity at x equals 5. But we created a function where we had two discontinuities, and we were actually able to remove our removable one and rewrite the function as a piecewise. Let's take a look at this example right here. It's determinative continuous. Again, we're just going to basically be doing the limit from the left and the right. So the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x. Again, this is what I hope to be true. This might not be true. And how did I figure out it's supposed to be a 1? I looked at the bounds, and that's what kind of gave it away. So let's look at the left first. The left piece is going to be the bottom piece. If I plug a 1 in here, I get 2 times 1 is 2 minus 5 is -3 equals, if I plug a 1 in the top function, so the top function is going to be 1 squared, which is 1, minus 3, that's just going to be 1 minus 3 is -2, so this is going to fail. So therefore, f of x is not continuous at x equals 1, but otherwise is continuous. Okay? So it's important that when we don't get discontinuity happy, when you're finding discontinuities, yes, it's important to note them, but also make sure you tell the problem that it's continuous everywhere else. So you did a good job, problem. You're just not continuous at x equals 1. Okay, let's try the bottom one. The bottom one here looks like a nice function. It's looking like we're checking 1 again. So let's do the limit as x approaches 1 from the left, and we're going to compare that to the limit as x approaches 1 from the right. And we're going to hope these are equal. Let's do the left first. The left is defined by the top piece. The top piece would be 1 squared is 1 plus 4 is 5 equals. The bottom piece is going to be 1 plus 4 is also 5. Neato. So this works. So the limit as x approaches 1 of f of x is 5. Does that equal f of 1? This is the question now. If this works, then we win. We have continuity. So the limit as we approach 1 of f of x is 5. And f of 1 is right here. Here's f of 1. You just plug in a 1 here, and you get 5. So yeah, we've got this thing. So f of x is continuous for all x values on its domain.